Welcome back to Practical PyTorch. This lesson opens the playlist on speed. Your model is slow and your first stopwatch is probably lying. We will learn to time a GPU honestly. Every number in this playlist comes from one GPU, an NVIDIA L4. We use that same GPU, so all the numbers stay comparable. Your first guess about the slow part is almost always wrong, and your first stopwatch is almost always lying. A GPU call is asynchronous. The line C equals A at B hands the work to the GPU. Then it returns to Python right away before the kernel has run. So a plain timer times the handoff, not the work. This is the same timing lesson from the CUDA course, now in Python. We will fix it 3 ways. We land on one number you can trust. This lesson has 3 parts. First, the async clock. We see why the CPU clock stops before the GPU does. Second, we time it honestly. We synchronize, warm up, and take the median. Third, the first call trap. The very first call pays a one-off setup cost. Part 1, the async clock. Let's see why there are really 2 clocks running. There are 2 timelines here. The top lane is the CPU. This is where your Python T0 and T1 marks live. The bottom lane is the GPU. This is where the real work happens. Python starts its clock at T0, near the left. A plumb tick drops from T0 down toward the GPU lane. But the kernel bar sits far to the right. The launch already returned to Python, and the kernel has not started. The Python timer stops almost at once. The T1 mark lands right next to T0. Its tick drops down, still far to the left of the kernel. The measured bracket runs from T0 to T1. It is tiny, and it ends long before the kernel begins. That short bracket is all a naive timer ever sees. The Python timer already stopped, but the kernel bar runs on. It reaches far past where the CPU bracket ended. This long bracket is the true work. It spans the whole kernel, many times wider than the measured one. The 2 brackets barely overlap. Without a synchronize, the naive timer underreports badly. Here it is 63.7 times too small. The fix is one line, synchronize. It tells Python to wait until the GPU is done. Now T1 slides all the way to the end of the kernel bar. A plumb line joins T1 to the kernel end. The 2 marks line up. The CPU clock finally measures the whole GPU work. Part 2, time it honestly. 3 small habits turn the lie into a number you can trust. Warm the GPU first. This line runs the matmul a few times. That makes the comparison fair. The cold first call comes later. Block A is the naive timer with no synchronize. It stops the moment the launch returns, so it lies about the work. Block B is honest. It calls synchronize before and after the matmul, so the reading spans the whole kernel. We use perf counter, a high-resolution wall clock, the same one the capture used. One reading can be noisy. Block C runs 10 warm-up iterations first. Those pay off the one-off costs. Then it runs 100 repeats. Each repeat is synchronized before and after the call. We report the median, not the mean. The median is the safe choice when one repeat spikes. This median is the number to quote. Now run all 3. The naive timer reads 0.172 milliseconds. That is the lie. It timed the launch. The honest single shot reads 10.966 milliseconds. The warmed median reads 10.938 milliseconds. The honest number is 63.7 times the naive one. The single shot and the median match closely. That agreement is how you know both are real. Quote the median. Every number here is measured on the L4. Part 3. The first call trap. One habit is left, and it is the easiest one to miss. One trap remains, timing the very first call. The random lines create the CUDA context by themselves. The first matmul pays a one-off setup. It runs CU, BLA's lazy init and kernel auto-tuning. That cost sits on top of the real work, so the surcharge is the library init, not the context. The warm-up loop clears those costs first. Then the second reading is the real steady-state cost. The two calls tell the whole story. The cold first call reads 73.199 milliseconds. That is mostly one-off setup, paid once. The warm call reads 11.138 milliseconds. That is the real per call cost. The cold call is 6.6 times the warm one. Almost all of that gap is one-off setup. Warm-up spends that cost before the clock starts, so it never lands in your number. Warm-up is part of the method, not an optimization. Let's review. A GPU call is asynchronous. It returns after the kernel is queued, not after it runs. A plain timer with no synchronize measures the launch. Here that was 63.7 times too small. Synchronize before and after gives one honest reading. Then warm up and take the median of many repeats. Never trust the first call. It pays one-off setup. Synchronize, warm up, repeat, take the median. Only then believe a number. Your turn. You wrap a matmul in perf counter calls with no synchronize. What did you actually measure, the work or something else? Pause and think it through. Okay, here it is. You measured the launch, not the work. The call queues the kernel and returns right away. So your clock stopped while the GPU was still busy. That was about 0.172 milliseconds here. The real matmul is about 11 milliseconds. Add synchronize before the second reading, then warm up and take the median. You can now time a GPU operation honestly. Next, we look at what actually happens when you call one. The line a plus b is not one thing. It is a lookup that ends in a compiled kernel, and that lookup costs you every single time. We open the dispatcher and follow one Python line down to its kernel. See you there.